Hey, Mr. Qualls, and what we're going to be talking about here for the next couple of minutes is the different sets of real numbers. Now, basically what we're going to do is we're going to take the idea of this number line that we have been using for all sorts of stuff, and we're going to really, go through a little bit of an analysis and talk about the different types of numbers there are on that number line. And I have some numbers written up here already, but what we need to do is figure out what kinds of numbers make all of the number, what types of numbers are there on the line and where are they? And can we nail down the different types of every number that is on the line? And we really can. So the first thing we're going to do is establish that the same that we've talked about before, and we're going to talk about the king, or the king or the queen, and we're going to mention every once in a while, what's the domain that we're talking about? Is this are these numbers under a restricted domain? Okay, is the set just anywhere, or is it is there a specialized domain of the numbers that we're talking about, right? And how many of those numbers there might be. So this is the real number line. Okay, so any number that we've ever used that you could put on the number line is a real number. Okay, now you might wonder, well, if we have real numbers, do we have numbers that aren't real? And we do. We have numbers that are called imaginary numbers. So there's real, and then there's imaginary numbers, and we'll get to that in a minute. Now, we're not going to do anything with the imaginary numbers. We're just going to realize that if there are real numbers, there must be numbers that aren't real numbers. And those are the imaginary numbers. And then there's a type of number called complex numbers, which are a combination of real numbers and imaginary parts. And those can be graphed differently on an axis with a real number this way and imaginary this. It gets much more complicated, and it's not the type of math that a lot of people end up working with. We just need to know right now that if we're talking about the real numbers, there must be others as well. Okay, and we're going to see an imaginary number here in just a little bit. So before we get too far, the goal of this lesson is to know that numbers that are not rational are called irrational. Okay, so the word rational, we're going to use that. Any number that can be written as a fraction or a ratio is a rational number. Any number that cannot be written as a ratio or a fraction is not rational, or what we call irrational. All right. The second part of that is to understand informally that every number has a decimal expansion, and that those rational numbers that have expansions, or all rational numbers have decimal expansions, those that repeat eventually, those that end, and we're going to be able to convert those that eventually repeat into a rational number. So basically, what we're looking at is, do all numbers have a decimal extension to them? What if that decimal extension is all zeros? What if it repeats? And what if it doesn't repeat? That's really what we're concerned with here. So let's look at these numbers through a thing. We're going to use a mathematical practice. Whoop, not modeling. Yours is not modeling. It is using structure. All right. So modeling was the one that I was doing a little while ago. I don't want to do any modeling here. I mean, I just changed into this t-shirt. Can't any moves on a catwalk in a t-shirt. Well, maybe you can, but not this guy. So what I'd like to start with here is the idea that if we're talking about real numbers, there are different types of real numbers on this real number line. And usually what we come up with first are the numbers that are easy to mess with. And they're the counting numbers. the 1, 2, 3, and so on. So we have 1, 2, 3, and 4, and so on. These numbers are whole. So we've got whole numbers as one of the types of numbers that are on this line. And that would be the 1, the 2. The 0 is not a whole number. The 0 is not a whole number. So the whole numbers do not include 0 or anything that's negative. You can't have -3 whole pizzas or 0 whole pizzas. Always think about pizza. You can have a whole pizza, or you can have 2 whole pizzas, or 3 or 4 or 500 whole pizzas. That sounds pretty sweet. But you can't have 0 whole pizzas. And none of the numbers between here are whole. So now what we've done is we've established that we're going to start down this line with these numbers, and they're going to be whole numbers. Now, what kind of other numbers do we need to include in this? Well, since I've already brought them up, how about the opposites of these numbers? But opposites of the whole numbers. So we're going to have -1, -2, -3. Maybe I should list them in the other order. How about that? So we've got -3, -2, -1, and then we've got 1, 2, and 3. So we've got these numbers and their opposites. So now we can have the other numbers that are opposites of the whole numbers. And then I would also make an argument that we can't just have these numbers and these without the separation that is between them. And that is going to be, these are all 1 apart. There's 1 from here to here, 1 to the 3, 1 to the 4. It's 1 to the -2, 1 to the -3. So these are all 1 apart on the number line. And the 0 is 1 away from this. And it's also 1 away from this. That's what makes this idea this much, is that distance from here to here is this, all right? So I would make the argument then that this is also one of this set of real numbers. So the first set of real numbers I was talking about is called whole numbers, which we use to count with. And then we've got the opposites of the whole numbers and the 0. And we're going to call these things integers. Integers. And they're the ones that we typically mark our coordinate planes with integers, things like that. Our number lines are marked with integers. Other things are the integers don't work for. The negative integers do not work for, how many times I went to the store since we left school. How many times have I made a video? I mean, those are all whole number ideas. The integers are for position compared to the 0. They are for graphing and that kind of stuff. The next set of things, now that we've established where all these little marks are, they're all 1 apart. Now we need to start looking at, well, what's between here? What kind of numbers are between here? What kind of numbers are between the 1 and the 2? Well, 1½ is between there. So I've got 1½ would be between there. 1 1/4. 1 1/4, 1 3/4. And so I've got all my fractional values that sit between here and then between here. In fact, there's an infinite number of fractional values that sit in here. Now, fractional values are also decimal. So this is 1.25, this is 1.5, and this is 1.75. So all of my fractional and all of my decimal pieces are all in here as well. So I'm going to refer to these things as my fractional pieces and my decimal pieces that end. But what I'm going to do is I'm going to call those my rational numbers. I'm going to call these rational. They're rational numbers. And the reason they are rational is because I can write them all as a fraction. So I can write 1.25 as a fraction. It's right there. 1.5 as a fraction, 1.75 as a fraction. I can write 3/2 as a fraction. So it is also a rational number. It is 1.5. I can write 1/3 as a as a fraction. So it is also a rational number. However, this fraction, when it's changed into a decimal, does not terminate like the rest of these that all have repeated decimals to it. This is a 0.25, and it has a decimal expansion of 1.25000000. So we just get rid of the zeros. This one has 1.5000. We just get rid of the zeros. Same with this one. 3/2 is 1.5 or 1.5, and it's got an expansion of zeros. So we just ignore those and say that it terminates. This one, however, does not terminate. It's 0.3333, and it just keeps going. So we're going to call that 0.3 repeating. And the repeating means that there is a decimal expansion. It's just 0.3, and it's threes forever. However, and it does not stop. However, it repeats. And since it repeats, we can write it as a fraction. Just like I did in that last, if we looked at that, if we had, what was it? If it was 0.7 repeating, and that 0.7 repeating, that is a non-terminating decimal. However, if it's 0.0 or 0.7 repeating, if it repeats, I can eventually turn this in with that complicated process I showed you, or 7/9, and even though it repeats, it still is a rational number. All right, so we have our whole numbers, we have our integers, which the whole numbers are over here, the integers are all down the line. The rational numbers fill in these gaps, and then the decimals that are still rational but they repeat, those are in there as well. And then we finally have these one little set of numbers, and it seems to be little because there's so few of them. However, there is an infinite number of these kinds of numbers, all right? And they are called irrational because I cannot write them as a fraction. And an irrational number, an example of an irrational number is something like the square root of 2. And if I look at the square root of 2, the square root of 2 is going to have to be between 1 and 2 because 1 squared is 1 and 2 squared is 4. So the square root of 2, the square root of 1 would be 1, the square root of 4 would be 2, so the square root of 2 has to be between these two numbers. And when we put that into a calculator, when you put your square root of 2 into a calculator, you come up with this number. 1.41421, and it just seems like it just goes on forever, and there is no repeating. It just goes on forever, and there's no repeating, so there's no pattern. And since it has a decimal expansion, but there's no pattern, we can't do anything with that. We cannot write this if I wanted 1.414213563. If the only way that I can put this back into a fractional form is to find the pattern and then use the pattern to make the fraction, there's no pattern here. Therefore, it's not rational. So it is irrational. Irrational. And the word rational means it's a ratio or a fraction. And if it's a fraction, it's rational. But if it is not rational, it's not a fraction. Therefore, it doesn't end and it doesn't repeat. Okay? But it's still on the number line. Okay? A number that you guys have been using using a very long time is pi. Pi Well, it's approximately equal to 3.14. The reason we use an approximation of 3.14 is because pi is really 3.14159, whatever it is. I can't write it all down. You know why? Because there's no pattern. And it doesn't terminate because it's irrational. It's an irrational number. But is it still on the number line? You bet it is. It's a real number because it's really close to 3.14. So if I wanted to put pi on the number line, I would go out 1, 2, and then I would find my 3. And then 1, 2, 3, and I would place it maybe right about here. And I would just say, well, there's pi. You might say, well, how do you know exactly where you hit it? I didn't. I covered an infinite number of points when I put that dot on there. I just know that pi is over there. Okay? And if I really wanted to get more exact, there's really no point to it. It's between the 3 and the 4. Much closer to the 3, however. Okay? So what we're going to do is a little exercise here. We're going to take these ideas of this, and keep in mind when we, when we're looking at this with the king here or the queen, and we were talking about domain, the real numbers or the whole numbers were only the domain. They were limited to the right side of the 0 and only for the whole numbers. The integers were both sides of the 0 and the 0, and so the domain of those numbers was just on the little tick marks that we put. However, when we started with the fractional numbers and the decimal numbers that end or repeat, which are rational numbers, the rational numbers filled in these gaps, and so the domain of the rational numbers is positive and negative, toward negative infinite and positive infinite, except for the places where the irrational numbers are. And there are an infinite number of irrational numbers, and those things do not count for that domain. However, when you add the irrational numbers to it, then the entire domain is taken by the real numbers. So I'm going to draw a little bit of a Venn diagram, which goes with the idea of us using structure to make sense of where these things are and how they're related to each other. And I'm going to draw a circle here, and I'm going to put whole numbers in there. Whole numbers. And then outside of that, I'm going to put integers. Integers. And then outside of that, we're going to put the rational numbers. We're going to put rational numbers over here. Okay? So these things are going to be rational. I might as well put the word numbers in there. Numbers. And then over here, I'm going to put irrational numbers. Irrational numbers. And then over top of this, real numbers. I used to talk about a joke, or I used to joke around with some classes in the past about what kinds of things, when we talk about irrational numbers. And, you guys know what irrational looks like. It's kind of like the way that you're, and I'm not to poke fun at any teachers, but typically English teachers, their behavior is just irrational. It's like weird. It's not like, are you basing this on any kind of logic or rational thought? Most of their decisions, they just go about their day like, and it really just drives me crazy. So what I'm going to do is I'm going to put, just to remind us, and then we're going to use this symbol later. I'm going to draw one of the. Now, this could be any of your English teachers. Look at her. That's a perm. They just can't help themselves. But there they are. Okay, and I'm going to draw her again a little bit so that it'll help us relate to our irrational numbers and what irrational numbers look like. So what I want you to do right now is realize that the whole numbers are also part of the integers, and the integers are also part of the rational numbers, and the rational numbers are part of the real numbers, and the irrational numbers are part of the real numbers. So the real numbers contain these, but then the integers and the whole numbers. So if you find a whole number and it's here, it's also in the integers. It's also in the rational numbers, and it's also a real number, but it's not an irrational number. If you identify an irrational number, it is only in the real numbers, irrational numbers and real numbers. It is not a rational number. It's not an integer, and it's not a whole number because it would be sitting over here. So what I want you to do is draw this rectangle on a piece of paper, put real number over the top, and all the numbers that we're, well, the numbers that we're talking about so far have been real numbers. We want real numbers in the top, rational numbers here, integers, whole numbers, irrational numbers. And I want you to pause this video. I want you to draw this, and I want you to pause this video, and I want you to look at all of these 14 numbers that I've got written on the side over here. I've got 14 numbers written right there. And what I want you to do is I want you to take those 14 numbers, and I want you to place them where you think they go in that diagram. All right? So for instance, if I made a decision that the 9 is, well, it's a real number. I know that because we're talking about real numbers, but the 9 is, it's a rational number, it's an integer, but it's also a whole number. So the number 9 is going to go right here. All right? So I want you to do that. I want you to place those things in there. I'm going to pause this video, and then I want you to pause the video, and then I want you to come back and we'll check to see what your answers are. Okay? Pause it now. And we're back. So what I'm going to go do is go through some of these things. If I look through 9, I'm going to look at each one of these things. Hopefully you made a decision on each one. So I'm going to go through them one at a time, and then I'm going to cross them off so we know what we're doing, okay? So we already did 9. So I'm just going to cross through that. 9 is a whole number, okay? Because it's repeating part of its decimal is 0, 0, 0, 0. So I don't need that on there. It's a whole number, it's an integer, and I could write it as a fraction if I wanted. 9 over 1, it's a whole number. Let's look at another one. Now, we already established that pi is an irrational number because you can't write it as a fraction. It's certainly not an integer or a whole number, but it is real. It's an irrational number. The reason it's an irrational number is because it has a decimal expansion, but the decimal expansion does not end and it does not repeat. Okay? Oh, let's go over to -3 here. -3, is -3 a whole number? No, because I can't have -3 whole pizzas. Is it an integer? Yes. And it's rational, so I'm going to put it right here. -3 goes right there. All right, 3 down, 11 to go. How about the next one? Oh, this one right here. Look, -5/9. -5/9. Now, if I made that into a decimal and looked at its decimal expansion, it would be 0.55555. So it's 0.5 repeating, and it's negative. So it can't be a whole number because it has a decimal piece. It can't be an integer. It is rational, however. So I'm going to put my -5/9, and I think, you know, it's easy to think that this is rational because ratio means fraction, and it's written as a fraction. So this is -5/9. It's going to go right here. So, hey, I looked at this one before, 0.3 repeating. Now, it's not an ending decimal, but now if it's not an ending decimal, it's not a whole number for sure because it's got a decimal piece. It's not an integer because we don't use it on the lines to mark things. And so now we need to just figure out, is it an irrational number or is it a rational number? Well, it's rational because even though the decimal expansion goes on forever, it repeats. And that means I can make it into a fraction, which means it is fractional, which means it's rational. So I'm going to put 0, 0.3 repeating in that section. Oh, some of these others are a little complicated. Hey, there's a decimal that ends. I know that that decimal that ends, so I'm going to put that one in my rational numbers, negative 5.84, slice. And then, 4.5, that's not a whole number or an integer, and it ends. That meets the same criteria that this one does. So I'm going to put 4.5 in there. Everything else up here. Oh, look, a ratio. It's a ratio. A ratio. So a ratio goes into 27 over 4. I don't even have to think about that one because it's a fraction. And there we go. So the others that are left, square root, or negative, square root of 100, square root of 25, these others all have to be simplified. Oh, except the 0. Now, the 0 needs to be placed. We know it's not irrational. It's a rational number because it has a decimal extension of 0.00000. I know some of you guys are not comfortable with that, but 0.0000, that's a decimal expansion, and it's 0, so we don't really care about it. 0 is not a whole number. It is an integer, however, because it helps me mark where things are on the number line. Okay? It is a positional idea. There we go. Now, like I was saying before, these 5 need to be simplified before I can put them in that thing, right? So let's look at the square root of 25. Now, the square root of 25 is either 5 or negative 5. The square root of 5, if I was to say the square root of 5, if I wanted the principal square root, which is the positive side of the square root, which is what is marked here because there's no positive or negative outside and I didn't tell you about it, so we're just going to go with the positive side. So the square root of 25 is a whole number because if we simplify that, it's 5. Now, I understand that you could have had 2 numbers here, positive one or a negative one, but this is marked here for just the principal square root. If it had been 5 or negative 5, I would have to move it out into the integers and not leave it in the whole numbers because then it could have been 5 and negative 5. So I would put it out in the integers, okay? Slice. Look at this one right here. Look at that donut. The negative square root of 100 is going to be, the square root of 100 is 10, and then the opposite of 10 is negative 10. So this number is really negative 10. It's not a whole number, it's an integer. But I had to simplify it before I could actually do the problem. We only have 2 left. All right, so I'm going to do this one. So what we were talking about last lesson about these kinds of numbers, what we can do here is leave the 9 on the bottom. What's the square root of 81? It is 9. What? This is a 1. So this is actually a whole number. So we're going to put the square root of, let me mark this again here. This should have been the square root of 100, negative square root of 100. And then this one is going to be the square root of 81 over 9 is really a whole number because the square root of 81 is 9. 9 over 9 is 1. That's a whole number because you can have a whole pizza. I must be hungry for pizza. All right. Now, the last 2 we have, square root of 17 and the square root of negative 25. I must have put them on there on purpose because there must be, that must be purposeful that I put those things on there, right? There must be something to talk about. Here's the square root of 17. Square root of 17. 4.1231056. There, boy, it sounds like there's a pattern there, right? No, there's no pattern. There is no pattern with this. It is an irrational number. It is an irrational number. It's just like your English teachers. It is an irrational number. There they are. The square root of 17 is an irrational number because when it is expanded decimally, if there's such a thing like that, it never quits and it doesn't repeat. Just like your English teachers. They never quit. And they just keep going and going and going. And they just don't repeat what they're talking. They've got new sarcasm and new ideas and new things for you to read. They just never stop. It never repeats. It just goes on and on. It's an irrational number. Okay? The last one we need to look at is negative, the square root of a negative 25. And I know a whole bunch of you are ahead of me on this, and good for you. This is a smart group of people. There is a very difficult problem here on this. Now, the square root of 25 is either 5, because 5 times 5 is 25. Square root of 25 could also be a negative 5 times a negative 5, which is also 25. And then, if we wanted to get a negative number underneath that radical, and we're thinking about something times itself has to be a negative 25, well, nothing times itself can end up being negative, because if they're both negative, it ends up being positive. If it's both positive, it ends up being positive. So what we're going to have to do for the 25 to be negative is have 5 and negative 5, and that is not two numbers that are the same, because they are on opposite sides of the zero, same absolute value. They're opposites of each other. They are not in the same position. They are not the same number. Therefore, this does not have an answer that we at this time can solve or can simplify. Now, in Algebra 2, you will be simplifying this. In fact, what happens is we take this idea right here and we split it to the square root of a negative 1 times the square root of 25, and then we call this thing I for imaginary. And so this is an imaginary number. So you can't put it on this block. It's a trick. So the negative square root of negative 25 for right now has to go out here with the imaginary numbers because it's not real. It can't sit on this. Okay? So there's a lot of information that I just went through here. We're going to be talking about these things a lot. I'm going from here on out. If I'm talking to you guys about numbers and we're questioning things, I'm going to ask, is this a rational number? Is this number irrational? Is this number rational? Is it irrational? Can you put it in fractional form? Is this a repeating decimal? Is it a non-terminating decimal? Is it terminating decimal? Is it irrational? Okay, so do your homework, turn it in, be nice to each other, and be good kids.